the infinity collapse, witnessing the birth of a supermassive black hole in the deepest reaches of space, where light from distant galaxies has traveled for billions of years to reach our instruments. The universe reveals its most profound secrets through the patient observations of those who seek to understand its mysteries. The James Webb Space Telescope, floating silently in the void, recently captured something unprecedented, a cosmic event so rare and magnificent that it challenges our understanding of how the universe creates its most extreme objects. Two ancient galaxies, born when the cosmos was young and stars first began to shine, are engaged in a gravitational dance that spans millions of years. As they spiral toward each other, their combined gravitational forces sculpt their gas and stars into a perfect infinity symbol, an elegant mathematical form written across the darkness in streams of glowing matter. At the heart of this celestial infinity sign, something extraordinary is taking place. The direct birth of a supermassive black hole from a collapsing cloud of primordial gas. This phenomenon, known as direct collapse, has been theoretical for decades, a mathematical possibility that could explain how the universe's most massive black holes came to exist so early in cosmic history. Unlike the familiar process where massive stars die and leave behind stellar mass black holes, direct collapse bypasses the stellar phase entirely, allowing pristine gas from the early universe to collapse directly into gravitational singularities millions of times more massive than our Sun. The observation of this infinity collapse represents more than a scientific discovery. It offers a meditation on the universe's capacity for creating order from chaos, beauty from violence, and structure from the seemingly random dance of matter and energy. As consciousness settles into contemplation of this cosmic event, there emerges a profound sense of witnessing creation itself, not the gentle formation of planets or the gradual accumulation of cosmic dust, but the violent birth of spacetime's most extreme curvature, where the familiar laws of physics stretch toward their breaking point and beyond. The ancient dance of galaxies. In the early universe, when the cosmos was barely 2 billion years old, and the first generation of galaxies were still young and metal-poor, the gravitational forces that would eventually sculpt the large-scale structure of the universe were already at work. The two galaxies, now locked in their cosmic embrace, began their approach across vast distances of space, their paths determined by the subtle gravitational influences of dark matter halos that extend far beyond their visible boundaries. Each galaxy carried within it the pristine material of cosmic creation, hydrogen and helium forged in the first minutes after the Big Bang, along with trace amounts of lithium created during the early nucleosynthesis epoch. This primordial composition, largely uncontaminated by the heavy elements produced in stellar cores, provided the perfect conditions for the extraordinary event that would unfold at their collision's heart. The gravitational interaction between these galactic titans operates on timescales that dwarf human comprehension, yet the forces involved are so immense that they reshape entire stellar populations and redirect the flow of interstellar gas across distances measured in hundreds of thousands of light years. As the galaxies approach each other, their mutual gravitational attraction accelerates their approach, while tidal forces begin to distort their original spiral structures into the elongated streams that will eventually form the infinity pattern. The dark matter halos surrounding each galaxy play a crucial role in this cosmic choreography, providing the gravitational scaffolding that guides the collision's evolution. These invisible structures, containing several times more mass than all the visible stars and gas combined, determine the encounter's geometry and timing. Their gravitational influence extends far beyond the galaxy's visible boundaries, creating a complex three-dimensional web of forces that orchestrates the collision's unfolding drama. Within each galaxy, billions of stars continue their nuclear burning, unaware of the cosmic forces that will soon reshape their galactic home. Star formation continues in the spiral arms, where gas clouds collapse under their own gravity to create new stellar nurseries. Yet these individual stellar processes, dramatic as they might seem on human scales, pale in comparison to the galactic scale forces that are beginning to dominate the evolution of both systems. The interstellar medium within each galaxy, the tenuous gas and dust that fills the space between stars, begins to respond to the gravitational perturbations long before the collision itself. Shock waves propagate through the gas clouds as the galaxy's gravitational fields overlap, compressing some regions and rarefying others. These perturbations trigger episodes of enhanced star formation in some areas, while quenching it in others, creating complex patterns of stellar birth and quiescence that reflect the chaotic nature of the approaching collision. The supermassive black holes that already exist at the centers of both galaxies, each containing millions of solar masses, begin to influence each other's accretion patterns as their host galaxies approach. The gravitational interaction between these central engines creates complex orbital dynamics that will eventually lead to their merger. But for now, they serve as gravitational anchors that help maintain the coherence of their respective galactic cores during the early phases of the collision. The magnetic fields threading through the interstellar medium of both galaxies become amplified and twisted by the tidal forces, creating complex topologies that will guide the flow of ionized gas during the collision's most violent phases. These magnetic structures, invisible to optical telescopes but detectable through radio observations, provide additional channels for energy transport and help regulate the rate at which gas can flow toward the collision's center. As the galaxies continue their approach, the first tendrils of gas begin to be stripped from their outer regions by tidal forces. These streams of matter, following complex trajectories determined by the combined gravitational field of both systems, mark the beginning of the infinity patterns formation. The gas follows elegant mathematical curves through space, creating graceful arcs that span hundreds of thousands of light years while converging toward the point where something unprecedented will soon emerge. The orbital velocities of stars within each galaxy begin to change as the systems approach, with some stellar populations gaining energy and moving to higher orbits, while others lose energy and spiral inward. This process of violent relaxation redistributes the gravitational binding energy of both systems, preparing them for the dramatic reorganization that will occur when their cores finally merge. Now, close the eyes and envision these ancient leviathans drawing together across cosmic time, their graceful spiral arms beginning to stretch and distort, streams of starlight and gas flowing between them like luminous rivers, all converging toward a moment of creation that will reshape the very geometry of spacetime. The formation of cosmic infinity as the gravitational embrace between the colliding galaxies tightens, their mutual tidal forces begin to sculpt matter into patterns of breathtaking mathematical beauty. The infinity symbol that emerges from this cosmic choreography represents far more than a simple coincidence. It embodies the universe's fundamental tendency to create order and symmetry, even amid the apparent chaos of galactic collision. The formation of this infinity pattern occurs through the precise orchestration of gravitational forces operating across multiple scales simultaneously. The dark matter halos of both galaxies create the large-scale gravitational architecture that determines the overall geometry of the collision, while the central supermassive black holes provide focal points around which matter can accumulate and organize into the characteristic figure-8 configuration. The gas streams that form the infinity symbol follow trajectories governed by the combined gravitational potential of both galaxies, their paths resembling the mathematical curves known as lemniscates. These graceful arcs of matter extend across hundreds of thousands of light years, each particle of gas following its own orbital path while contributing to the larger pattern that emerges from their collective motion. The luminosity of these gas streams comes from multiple sources, creating a complex spectrum of electromagnetic radiation that tells the story of the collision's evolution. Shock heating from compression waves generates thermal emission across the infrared and optical bands, while magnetic field interactions create synchrotron radiation in the radio spectrum. The combination of these emission mechanisms paints the infinity symbol in light across multiple wavelengths, making it visible to the sensitive instruments aboard the James Webb Space Telescope. The symmetry of the infinity pattern reflects the nearly equal masses of the two colliding galaxies, a rare configuration that allows for the stable formation of such elegant structures. In most galactic collisions, the mass ratio between the participants is significantly unequal, leading to more chaotic and asymmetric outcomes. The precise balance achieved in this system creates the gravitational equilibrium necessary for the infinity pattern to maintain its coherence over the extended timescales required for the central collapse to proceed. Within the infinity loops, smaller scale structures develop as gas clouds compress and fragment under their own gravity. These secondary condensations create complex hierarchical patterns reminiscent of fractal geometry, with self-similar structures appearing at multiple scales. The largest condensations span thousands of light years, while the smallest detectable structures are still hundreds of times larger than individual solar systems. The magnetic fields threading through the infinity streams play a crucial role in determining the flow patterns and energy dissipation rates within the colliding gas. These fields, frozen into the conducting plasma, are amplified and twisted by the differential motion of the gas streams, creating complex topologies that channel energy transport and help regulate the rate of angular momentum loss that drives the inward flow of matter. The intersection point at the center of the infinity symbol marks the location where the most extraordinary physics will unfold. Here, matter from both galaxies converges along trajectories that bring it closer to gravitational equilibrium, while simultaneously removing the angular momentum that would otherwise prevent collapse. The geometry of the infinity pattern naturally focuses matter toward this central point, while providing mechanisms for angular momentum transport that allow the accumulation of enormous masses. The temperature structure within the infinity streams reveals the complex thermodynamics of the collision process. While the bulk of the gas remains relatively cool, around 10,000 degrees, the shock fronts and magnetic reconnection events create localized heating that can drive temperatures to millions of degrees. These hotspots serve as beacons that illuminate the collision's internal structure while providing the thermal pressure that supports the gas streams against gravitational collapse. The chemical composition of the infinity streams reflects their origin in the pristine, interstellar medium of early galaxies. The gas is predominantly hydrogen and helium, with only trace amounts of heavier elements, creating an environment remarkably similar to the primordial conditions that existed shortly after the Big Bang. This chemical purity is essential for the direct collapse process, as the absence of heavy elements prevents efficient cooling that would otherwise fragment the gas into smaller stellar mass objects. The evolution of the infinity pattern occurs on timescales of several million years, during which the overall configuration remains remarkably stable while the internal structure continuously evolves. Gas flows inward along the streams while new material is continuously fed from the outer regions of both galaxies, maintaining the pattern's luminosity and structural integrity throughout the collision's most active phase. The observational detection of this infinity pattern required the extraordinary sensitivity and resolution of the James Webb Space Telescope, combined with complementary observations from the Chandra X-ray Observatory, to reveal the high-energy processes occurring within the collision. The infrared capabilities of JWST proved particularly valuable for penetrating the dust lanes that obscure much of the action in optical wavelengths, while Chandra's X-ray vision revealed the hot gas and energetic phenomena that trace the most violent aspects of the collision. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars, the gathering storm of primordial matter, at the heart of the cosmic infinity, where the gravitational forces of two ancient galaxies converge with mathematical precision, a vast accumulation of primordial matter begins to gather with ominous inevitability. This is not the gradual accretion of dust and gas that typically feeds stellar formation, but rather a catastrophic concentration of material on scales that dwarf the formation of entire stellar clusters. The matter flowing toward the collision center carries with it the chemical signature of the early universe, a composition dominated by hydrogen and helium, with only the faintest traces of heavier elements. This pristine material, largely unchanged since the epoch of recombination when the universe first became transparent to light, provides the perfect conditions for the direct collapse scenario that theoretical astrophysicists have long predicted but never observed. The absence of significant heavy element contamination proves crucial to the unfolding drama, as these elements would normally serve as efficient coolants that allow gas clouds to fragment into smaller, stellar mass objects. Without carbon, oxygen, and other metals to radiate away thermal energy, the accumulating gas cannot cool below a critical temperature threshold of around 10,000 degrees. This thermal floor prevents fragmentation and maintains the coherence of the massive gas cloud as it contracts under its own gravity. The mass accumulation rate at the collision center reaches extraordinary levels, with the equivalent of thousands of solar masses flowing inward every year. This rate far exceeds the accretion rates typically associated with stellar formation or even the feeding of existing supermassive black holes. The gravitational architecture of the infinity pattern naturally funnels matter from across both galaxies toward the central convergence point, creating a cosmic feeding mechanism of unprecedented efficiency. As the central gas cloud grows more massive, its internal gravitational field strengthens, accelerating the infall of additional material in a runaway process that becomes increasingly difficult to halt. The cloud's own gravity begins to dominate over the thermal pressure that initially supported it against collapse, marking the transition from a stable accumulation phase to the inexorable descent toward gravitational singularity. The thermal structure of the accumulating cloud reveals the complex balance between gravitational heating and radiative cooling that determines its evolutionary path. As gas falls deeper into the gravitational potential well, it gains kinetic energy that converts to thermal energy through shock heating. However, the low metallicity of the gas limits its cooling efficiency, allowing temperatures to rise to levels that would normally trigger nuclear fusion in stellar cores. The magnetic field structure within the central cloud becomes increasingly complex as the infalling gas brings with it the frozen-in magnetic field lines from the infinity streams. These fields become compressed and amplified as the gas density increases, creating magnetic pressure that temporarily slows the collapse while the field lines reconnect and reorganize into more stable configurations. The rotation rate of the central cloud presents one of the most critical factors determining the success of the direct collapse process. Too much angular momentum would cause the cloud to flatten into a disk and fragment into smaller objects, preventing the formation of a supermassive black hole. The infinity pattern's geometry naturally extracts angular momentum from the infalling gas through gravitational torques, allowing matter to spiral inward while shedding the rotational energy that would otherwise halt the collapse. The size scale of the central accumulation grows to encompass regions comparable to entire stellar clusters, with the gravitational influence of the central mass concentration extending across hundreds of light years. Within this vast region, the normal processes of stellar formation are suppressed by the intense tidal forces and elevated temperatures that characterize the environment of direct collapse. The pressure waves generated by the continuing infall of matter create a complex acoustic environment within the central cloud, with sound waves propagating through the hot gas at velocities approaching the speed of sound in the medium. These acoustic oscillations help redistribute energy and momentum throughout the cloud while providing observational signatures that reveal the internal dynamics of the collapse process. The opacity of the central cloud to its own thermal radiation becomes a crucial factor as the collapse progresses. The increasing density and temperature create conditions where the gas becomes optically thick to its own radiation, trapping thermal energy within the cloud and accelerating the heating process. This radiative trapping marks the beginning of the final phase of collapse, when thermal pressure can no longer provide effective support against gravity. The gravitational potential well created by the central mass concentration begins to influence the broader structure of both galaxies, creating tidal streams and disrupting stellar orbits across regions spanning tens of thousands of light years. This gravitational influence grows stronger as more mass accumulates at the center, eventually becoming powerful enough to reshape the internal structure of both colliding galaxies. The threshold of no return. As the central mass concentration approaches the critical threshold for gravitational collapse, the physics governing its evolution enters a regime where general relativity begins to dominate over Newtonian mechanics. The accumulated matter, now containing several million times the mass of the Sun concentrated within a region smaller than a typical stellar cluster, creates a gravitational field so intense that space-time itself begins to curve significantly around the collapsing object. The event horizon that will eventually define the boundary of the newly formed black hole does not yet exist, but the gravitational field strength at the cloud's center approaches the values where relativistic effects become important. Light rays passing near the central mass concentration begin to follow curved paths, while clocks within the gravitational field appear to run slower when observed from regions of weaker gravity. The hydrodynamics of the collapsing gas cloud enter a regime where radiation pressure becomes comparable to gas pressure, creating a complex environment where photons and matter are tightly coupled through frequent interactions. The mean free path of photons within the dense core shrinks to microscopic scales, effectively trapping radiation within the collapsing material. and preventing it from carrying away the thermal energy that might otherwise halt the collapse. The nuclear physics within the collapsing core reaches conditions where hydrogen fusion could theoretically begin, but the rapid pace of gravitational collapse prevents the establishment of the hydrostatic equilibrium necessary for stable stellar burning. Instead of igniting as a massive star, the central object continues its inexorable contraction toward densities that exceed those found in the cores of the most massive stars. The quantum mechanical properties of matter begin to play a role as the collapse proceeds toward ever higher densities. Electron degeneracy pressure, which normally provides support in white dwarf stars, proves insufficient to halt the collapse of such a massive object. Even neutron degeneracy pressure, which supports neutron stars against gravitational collapse, cannot provide adequate support against the immense gravitational forces generated by millions of solar masses concentrated in an increasingly small volume. The general relativistic effects become increasingly important as the collapse accelerates, with the gravitational time dilation causing events near the center to appear increasingly slow when observed from distant locations. This temporal distortion creates observational challenges for detecting the final moments of collapse, as the light signals carrying information about the central regions become increasingly redshifted and delayed. The formation of an apparent horizon marks a crucial milestone in the collapse process, representing the surface beyond which light signals can no longer escape to distant observers. This apparent horizon forms before the true event horizon of the final black hole, growing outward as more matter falls through it and becomes causally disconnected from the external universe. The accretion shock that forms as infalling matter encounters the increasingly dense central core, creates a complex radiative environment where high-energy photons are produced through thermal emission and magnetic acceleration processes. These photons provide some of the last observational signatures of the collapse process before the formation of the event horizon renders the central object invisible to direct observation. The angular momentum of the collapsing matter plays a crucial role in determining the final properties of the black hole that will emerge from the collapse. The efficient extraction of angular momentum by the infinity pattern's gravitational torques allows the formation of a relatively non-rotating black hole, in contrast to the highly spinning black holes that might result from other formation mechanisms. The magnetic field threading through the collapsing matter becomes frozen into the plasma and compressed to enormous field strengths as the collapse proceeds. These intense magnetic fields may play a role in launching relativistic jets during the final phases of collapse, providing additional mechanisms for energy and angular momentum transport that influence the efficiency of the direct collapse process. The thermodynamic properties of the collapsing matter approach the regime where radiation pressure dominates over gas pressure, creating conditions similar to those found in the cores of the most massive stars, but on scales millions of times larger. This radiation-dominated environment creates unique observational signatures that distinguish direct collapse from other black hole formation mechanisms. The neutrino emission from the collapsing core reaches enormous levels as nuclear reactions proceed in the extreme temperature and density environment, creating a brief but intense burst of neutrino radiation that carries away a significant fraction of the gravitational binding energy released during collapse. These neutrinos provide the only direct window into the physics occurring within the opaque central regions during the final moments before event horizon formation. Now, feel the approach of this cosmic threshold where matter reaches the point of no return, where space-time itself begins to curve into the abyss that will swallow light and time, where the universe prepares to birth one of its most extreme creations, the birth of darkness. In the final moments before the event horizon forms, the collapsing matter experiences conditions so extreme that they challenge the boundaries of known physics. The density at the core approaches values where quantum effects and general relativity must be considered simultaneously, entering the realm of quantum gravity, where current theories provide only tentative guidance about the nature of physical processes. The formation of the event horizon occurs not as a sudden transition, but as a gradual emergence, with the surface of no return growing outward as more matter falls through it and becomes causally disconnected from the external universe. This process creates a black hole whose mass continues to grow even as its defining boundary expands to encompass an ever larger region of spacetime. The gravitational waves generated by the asymmetric collapse and the continuing infall of matter propagate outward at the speed of light, carrying information about the final moments of collapse to distant observers who can no longer receive electromagnetic signals from the central regions. These ripples in spacetime itself provide the last direct observational evidence of the physical processes occurring within the newly formed black hole's vicinity. The accretion disk that forms from the remaining infalling matter begins to exhibit the characteristic properties that will mark this object as an active galactic nucleus for millions of years to come. The gravitational energy released as matter spirals into the black hole creates luminosities that will eventually outshine the combined light of billions of stars, transforming the collision site into one of the most energetic objects in the observable universe. The relativistic jets that emerge from the black hole's polar regions carry away angular momentum and energy at velocities approaching the speed of light, creating narrow beams of high-energy particles and radiation that can be detected across cosmic distances. These jets serve as beacons that announce the birth of the new black hole to observers throughout the universe, while providing mechanisms for feedback that will influence the subsequent evolution of both host galaxies. The surrounding space-time geometry settles into the characteristic Schwarzschild or Kerr metric that describes the gravitational field of a black hole, creating a permanent distortion in the fabric of space and time that will persist for billions of years. This geometric distortion affects the motion of all matter and energy in the black hole's vicinity, creating the complex orbital dynamics that characterize active galactic nuclei. The information paradox associated with black hole formation manifests in its most extreme form during direct collapse, where enormous amounts of matter and the information it contains disappear behind the event horizon in a cosmically brief period. The quantum mechanical implications of this information loss remain one of the most profound unsolved problems in theoretical physics. The thermodynamic properties of the newly formed black hole follow the laws of black hole thermodynamics, with the event horizon area providing a measure of the black hole's entropy and its surface gravity determining its Hawking temperature. However, for a supermassive black hole of several million solar masses, the Hawking temperature is so low that thermal evaporation will require times longer than the current age of the universe to become significant. The no-hair theorem of general relativity ensures that the newly formed black hole quickly settles into a state characterized only by its mass, electric charge, and angular momentum, with all other details about the matter from which it formed becoming irrelevant to its external gravitational field. This simplification transforms the complex hydrodynamics of the collapse into the elegant geometry of curved spacetime, The tidal forces in the vicinity of the black hole's event horizon create spaghettification effects that stretch infalling matter into long, thin streams as it approaches the point of no return. These tidal effects become increasingly important for smaller objects falling into the black hole, while larger gas clouds can cross the event horizon relatively intact due to their extended size compared to the tidal radius. The frame dragging effects associated with the black hole's rotation create a region around the event horizon where spacetime itself is forced to rotate, carrying matter and energy along with the geometric distortion. This ergosphere provides additional mechanisms for energy extraction that will influence the long-term evolution of the accretion flow and jet production. The causal structure of spacetime around the newly formed black hole creates regions where cause and effect relationships become ambiguous, with closed time-like curves and other exotic phenomena emerging in the strong field regime near the event horizon. These effects highlight the fundamental changes in the nature of space and time that occur in the vicinity of such extreme gravitational fields. The observational signatures of the newly formed black hole will evolve over millions of years as it continues to accrete matter and interact with its environment. The initial period of rapid accretion creates quasar-like luminosities that gradually decline as the available fuel supply is consumed or expelled by feedback processes, eventually leaving behind a relatively quiet, supermassive black hole that will serve as the gravitational anchor for future galactic evolution. The ripples through spacetime. The birth of the supermassive black hole sends gravitational waves propagating outward through the fabric of spacetime itself, carrying with them the signature of one of the universe's most dramatic creation events. These ripples in the geometry of space and time travel at the speed of light, spreading the news of the black hole's formation across cosmic distances while providing unique observational windows into the physics of extreme gravitational collapse. The gravitational wave emission from direct collapse differs significantly from the signals produced by stellar mass black hole mergers or neutron star collisions. The much larger mass scale and extended duration of the collapse process create gravitational waves with characteristic frequencies and amplitudes that reflect the unique physics of supermassive black hole formation. These signals encode information about the collapse dynamics that cannot be obtained through electromagnetic observations alone. The frequency spectrum of the gravitational waves reflects the various phases of the collapse process, from the initial accumulation of matter through the final formation of the event horizon. Low-frequency components correspond to the large-scale motions of matter during the early phases of collapse, while higher frequencies emerge from the increasingly rapid dynamics as the matter approaches the point of no return. The amplitude of the gravitational wave signal depends on the efficiency of the collapse process and the asymmetries in the matter distribution during the final phases. Unlike the symmetric collapse assumed in many theoretical models, the real collapse process involves turbulence, magnetic fields, and rotation that create departures from perfect spherical symmetry and enhance the gravitational wave emission. The polarization properties of the gravitational waves provide additional information about the three-dimensional structure of the collapse and the orientation of the collapsing system relative to Earth. These polarization signatures allow observers to reconstruct the geometry of the collapse process and distinguish between different theoretical models of direct black hole formation. The detection of gravitational waves from direct collapse events requires next-generation gravitational wave observatories with enhanced sensitivity at the low frequencies characteristic of supermassive black hole formation. The Laser Interferometer Space Antenna, LISA, and other proposed space-based detectors will provide the necessary sensitivity to observe these signals from cosmological distances. The propagation of gravitational waves through the intervening cosmic medium provides additional scientific information about the structure and evolution of the universe between the source and observer. The waves interact weakly with matter along their path, making them excellent probes of cosmic structure formation and the distribution of dark matter on large scales. The memory effect associated with gravitational wave propagation creates permanent displacements in the positions of test masses after the wave has passed, providing a lasting record of the gravitational wave burst that can be detected by sufficiently sensitive instruments. This effect offers additional observational signatures that complement the oscillatory components of the gravitational wave signal. The energy carried away by gravitational waves during the collapse process represents a significant fraction of the total binding energy released, potentially reaching several percent of the rest mass energy of the collapsing matter. This energy loss affects the final mass of the black hole and influences the efficiency of the direct collapse mechanism. The beaming effects associated with gravitational wave emission from rotating sources create directional patterns in the radiated energy that depend on the viewing angle and the rotation rate of the collapsing object. These effects must be considered when interpreting observational data and estimating the intrinsic properties of the collapse from gravitational wave measurements. The interaction between gravitational waves and electromagnetic radiation in the vicinity of the collapsing object creates subtle correlations between the gravitational and electromagnetic signals that provide additional diagnostic information about the collapse physics. These correlations are particularly important during the final phases when electromagnetic signals become increasingly redshifted and difficult to observe. The cumulative effect of gravitational wave emission from multiple direct collapse events throughout cosmic history contributes to the stochastic gravitational wave background that pervades the universe. This background radiation carries statistical information about the population of supermassive black holes and their formation mechanisms across cosmic time. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments, a quiet echo beneath the stars. The cosmic implications of direct genesis. The successful observation of direct collapse black hole formation transforms theoretical predictions into observational reality, opening new chapters in understanding how the universe creates its most extreme objects. During the earliest epochs of cosmic evolution, this discovery resolves long-standing puzzles about the existence of supermassive black holes in the early universe, while simultaneously raising new questions about the prevalence and conditions required for such extraordinary events. The timing of this observed collapse, occurring when the universe was only 2 billion years old, demonstrates that supermassive black holes can form much more rapidly than previously thought possible through traditional accretion mechanisms. This rapid formation helps explain the existence of quasars at high redshifts, where supermassive black holes containing billions of solar masses appear to have formed within the first billion years after the Big Bang. The chemical composition requirements for direct collapse pristine gas with minimal heavy element contamination place important constraints on the environments where such events can occur. These conditions become increasingly rare as cosmic evolution proceeds and stellar nucleosynthesis enriches the interstellar medium with metals, suggesting that direct collapse may have been more common in the early universe than in more recent epochs. The role of galaxy mergers in triggering direct collapse events highlights the importance of large-scale structure formation in determining where and when supermassive black holes can form through this mechanism. The collision of massive metal-poor galaxies creates the unique combination of high gas density and efficient angular momentum removal necessary for direct collapse to succeed. The observational techniques that enabled this discovery, combining infrared observations from the James Webb Space Telescope with X-ray data from Chandra, demonstrate the power of multi-wavelength astronomy for studying extreme astrophysical phenomena. Future observations of similar events will require coordinated campaigns using multiple space-based observatories to capture the full range of physical processes involved. The rarity of direct collapse events, even in the early universe, suggests that most supermassive black holes form through alternative mechanisms such as the growth of stellar mass black hole seeds or intermediate mass black hole mergers. Understanding the relative importance of different formation channels remains a key challenge for theories of supermassive black hole demographics and cosmic structure formation. The feedback effects from the newly formed supermassive black hole will profoundly influence the subsequent evolution of both host galaxies, regulating star formation and potentially triggering or quenching stellar birth across vast regions. These feedback mechanisms play crucial roles in establishing the correlations between supermassive black hole masses and the properties of their host galaxy bulges. The gravitational influence of the central supermassive black hole will reshape the orbital structure of both galaxies as they complete their merger, creating a spheroidal remnant with dynamical properties that reflect the violent history of its formation. The stellar populations and chemical evolution of this merger remnant will preserve signatures of the direct collapse event for billions of years. The implications for cosmology extend beyond individual black hole formation to questions about the early universe's global properties and evolution. The existence of direct collapse events provides constraints on the primordial power spectrum, the nature of dark matter, and the thermal history of the intergalactic medium during the epoch of reionization. The information content preserved in the gravitational wave signals from direct collapse events offers new possibilities for testing general relativity in the strong field regime and searching for signatures of physics beyond the Rhine from Ceres Standard Model. These extreme environments provide natural laboratories for exploring quantum gravity effects that cannot be reproduced in terrestrial experiments. The discovery opens new research directions in computational astrophysics, requiring sophisticated simulations that capture the complex interplay between gravity, hydrodynamics, radiation transport, and magnetic fields during the collapse process. These numerical models must span enormous dynamic ranges in space and time, while incorporating quantum mechanical and relativistic effects. The philosophical implications of witnessing the birth of spacetime's most extreme curvature invite contemplation of the universe's creative potential and the emergence of complexity from apparent simplicity. The transformation of primordial gas into a gravitational singularity represents one of nature's most dramatic phase transitions, challenging human intuition about the relationship between matter and spacetime. Now, let awareness settle into the magnitude of this cosmic revelation, feeling how the universe demonstrates its capacity to create the most extreme objects through elegant gravitational choreography, where ancient galaxies dance together to birth the darkness that will anchor future cosmic evolution. The eternal dance of creation and destruction In the aftermath of the supermassive black hole's birth, the cosmic infinity that catalyzed its formation begins to evolve into new configurations that will shape the future history of both galaxies and their newly merged system. The gravitational architecture that once funneled primordial matter toward direct collapse now serves as the framework for ongoing accretion processes that will feed the central black hole for millions of years to come. The accretion disk that forms from the remaining infalling matter settles into a quasi-steady state where gravitational energy release balances radiative losses, creating a luminous, active galactic nucleus that will be visible across cosmic distances. The efficiency of this energy conversion process approaches theoretical limits, with a significant fraction of the rest mass energy of infalling matter being converted to electromagnetic radiation through gravitational acceleration and magnetic field interactions. The relativistic jets that emerge from the black hole's vicinity carry energy and momentum far beyond the boundaries of the merged galaxy system, creating cavities in the surrounding intergalactic medium and influencing star formation processes across regions spanning millions of light years. These jets serve as cosmic transmitters that broadcast the existence of the newly formed black hole throughout the local universe. The feedback mechanisms initiated by the active galactic nucleus create complex cycles of heating and cooling in the surrounding gas that regulate the rate of subsequent star formation and black hole growth. These feedback processes operate across multiple scales, from the immediate vicinity of the black hole where radiation pressure expels gas, to galaxy-wide scales where jet-driven shocks heat the interstellar medium and suppress cooling flows. The gravitational wave emission continues as the black hole accretes matter and potentially merges with other black holes in the system, creating an ongoing source of space-time perturbations that will contribute to the cosmic gravitational wave background. The detection of these continuing signals provides long-term monitoring capabilities for studying black hole growth and environmental interactions. The chemical evolution of the merged galaxy system reflects the complex interplay between stellar nucleosynthesis, supernova explosions, and black hole feedback processes. The enhanced star formation triggered by the galaxy collision creates new stellar populations with distinct chemical signatures, while the central black hole's activity influences the retention and distribution of metals throughout the system. The dynamical evolution of stellar orbits within the merged system creates a complex gravitational environment where some stars are scattered to large distances while others spiral inward toward the central black hole. This gravitational processing redistributes stellar populations and creates tidal disruption events when stars pass too close to the black hole's tidal radius. The magnetic field structure of the merged system undergoes dramatic reorganization as the collision compresses and twists field lines, while the central black hole's rotation generates new magnetic configurations. These evolving magnetic fields influence particle acceleration processes and create the conditions necessary for sustained jet activity over cosmic timescales. The thermal history of the gas component reflects the competing influences of gravitational heating, radiative cooling, and energy injection from stellar feedback and black hole activity. The temperature and density structure that emerges from this complex interplay determines the efficiency of subsequent star formation and the long-term evolution of the galaxy's gas content. The observational evolution of the system provides a natural laboratory for studying the co-evolution of supermassive black holes and their host galaxies over cosmic time. The brightness variations, spectral changes, and morphological evolution offer direct insights into the physical processes that establish the correlations between black hole mass and galaxy properties that characterize the local universe. The information preservation aspects of the black hole's formation and growth raise profound questions about the nature of space-time and the ultimate fate of information that falls beyond the event horizon. The quantum mechanical implications of direct collapse events provide new contexts for exploring the black hole information paradox and the holographic principle that may govern the relationship between bulk and boundary physics. The cosmic recycling processes initiated by the black hole's activity ensure that matter and energy are redistributed throughout the universe, rather than permanently sequestered behind the event horizon. The jets, winds, and radiation from the active galactic nucleus return processed material to the intergalactic medium, where it becomes available for future episodes of star formation and black hole growth. The legacy of the direct collapse event will persist throughout the cosmic future as the black hole continues to grow and influence its environment across billions of years. The gravitational anchor it provides will shape the assembly of future galaxy clusters and the large-scale structure formation processes that determine the universe's ultimate architectural destiny. The philosophical meditation on witnessing cosmic creation unfolds through contemplation of how the universe continuously transforms itself through cycles of construction and dissolution. The direct collapse represents not an ending, but a beginning, the birth of a gravitational organizing principle that will influence cosmic evolution for eons to come, while serving as a reminder of the creative potential inherent in even the most extreme physical processes. The mathematical beauty of the infinity pattern that catalyzed this creation event speaks to deeper symmetries in the universe's organizational principles, suggesting that even the most violent cosmic processes follow elegant geometric relationships that connect the microscopic and macroscopic scales of physical reality. This mathematical harmony provides aesthetic satisfaction that transcends purely scientific understanding. The temporal perspective required to appreciate direct collapse processes spanning millions of years for the collision and collapse, while extending billions of years into the future for the resulting evolution, expands human consciousness beyond ordinary temporal boundaries and invites contemplation of existence on cosmic scales where individual lifetimes become vanishingly brief moments in much larger stories. The interconnectedness revealed by this cosmic event demonstrates how local processes in one region of space and time can have far-reaching consequences that influence the evolution of structure across vast regions of the universe. The gravitational waves, electromagnetic radiation, and material outflows from the direct collapse connect this single event to the broader cosmic web of causation and influence. The silent witness of deep space. In the profound quietude that follows the cosmic drama of direct collapse, where the universe has succeeded in creating one of its most extreme objects from the gentle collision of ancient galaxies, there settles a peace that encompasses both the violence of creation and the eternal serenity of spacetime's deepest truths. The James Webb Space Telescope continues its patient vigil, recording the aftermath of this unprecedented event with instruments sensitive enough to detect the whisper of photons that have traveled billions of years to reach its mirrors. The black hole, now established as a permanent feature of the cosmic landscape, begins its long existence as a gravitational anchor that will influence the evolution of matter and energy across vast regions of space and time. Its presence creates a fixed point around which future cosmic evolution will organize itself, a gravitational lighthouse whose influence extends far beyond its immediate environment to shape the assembly of galaxy clusters and the flow of dark matter throughout the cosmic web. The infinity pattern that gave birth to this cosmic giant gradually dissipates as the galaxy merger reaches completion, its elegant mathematical form dissolving into the more chaotic structures that characterize post-collision galactic remnants. Yet the geometric beauty that briefly graced this region of space has served its purpose, creating the conditions necessary for one of the universe's most remarkable creative acts, while demonstrating the deep mathematical principles that govern cosmic evolution. The electromagnetic radiation streaming away from the active galactic nucleus carries information about the black hole's properties and environment to observers throughout the universe, creating a broadcast signal that will persist for millions of years as matter continues to fall into the gravitational abyss. This radiation serves as both announcement and invitation, declaring the existence of the new black hole while providing detailed spectroscopic information about the physical conditions in its vicinity. The gravitational influence of the supermassive black hole reaches across millions of light years, affecting the orbital motions of gas clouds and star clusters throughout the merged galaxy system. This gravitational choreography creates new patterns of matter flow and energy distribution that will influence star formation rates and chemical evolution processes for billions of years, establishing the black hole as a primary driver of galactic evolution. The relativistic jets emerging from the black hole's polar regions carve channels through the intergalactic medium, creating vast cavities filled with high-energy particles and magnetic fields. These jet-blown bubbles serve as monuments to the black hole's power, while providing heating mechanisms that influence the thermal state of gas across cosmic distances, demonstrating how local processes can have global consequences. The gravitational wave signals continue to propagate outward through spacetime, carrying with them the permanent record of the collapse event encoded in the geometric distortions of space and time itself. These ripples will travel until they reach the boundaries of the observable universe, spreading news of the black hole's birth to any civilization capable of detecting such subtle space-time perturbations. The chemical signatures left by the collapse process become embedded in the stellar populations and gas clouds throughout the region, creating isotopic anomalies and elemental abundance patterns that will preserve evidence of the direct collapse event long after its electromagnetic signatures have faded. These chemical fossils provide permanent records that future astronomers might discover and interpret billions of years in the future. The magnetic field configurations established during the collapse and its aftermath create long-lived structures that guide particle acceleration and energy transport processes throughout the merged galaxy system. These magnetic highways and barriers influence the propagation of cosmic rays and the distribution of high-energy phenomena across vast regions of space. The thermal history written in the gas temperature and density distributions reflects the complex interplay of heating and cooling processes that accompanied the black hole's birth and early evolution. This thermal archaeology preserves information about energy injection rates, shock propagation, and radiative transfer processes that characterized the collapse environment. The dynamical memories encoded in stellar orbital distributions throughout the merged system preserve kinematic evidence of the violent relaxation processes that redistributed gravitational binding energy during the collision and collapse. These orbital fossils provide lasting testimony to the gravitational chaos that preceded the establishment of the current equilibrium configuration. The observational legacy of this event extends beyond its immediate scientific impact to influence future generations of astronomical instruments and theoretical frameworks. The detection techniques and analysis methods developed to study direct collapse will enable similar discoveries throughout the universe, gradually building a statistical understanding of supermassive black hole formation mechanisms. The philosophical implications continue to resonate through contemplation of how the universe creates order from chaos, structure from randomness, and meaning from the seemingly purposeless dance of matter and energy. The direct collapse represents a cosmic meditation on creativity itself, the emergence of new forms of organization from the interaction of simple physical principles operating under extreme conditions. Now, allow consciousness to drift with these cosmic currents, feeling the profound peace that emerges when creation completes its work, when the universe demonstrates its capacity to birth the most extreme objects through the gentle collision of ancient worlds, when space-time itself becomes the canvas for artistic expression on the grandest possible scale, the eternal rest of cosmic time. As awareness settles into the vast quietude that encompasses this cosmic event, there emerges a profound sense of completion, not the ending of a story, but the establishment of a new equilibrium that will persist across cosmic ages. The supermassive black hole, born from the elegant collision of ancient galaxies, now exists as a permanent feature of spacetime's architecture, a gravitational sculpture carved from the fabric of existence itself through the patient operation of physical law. The consciousness that contemplates this cosmic birth finds itself synchronized with timescales that transcend human experience, where millions of years compress into moments of creation, while billions of years stretch ahead as chapters yet to be written in the black hole's ongoing story. This temporal expansion of awareness creates a meditative state where the boundaries between observer and observed, between local and cosmic, between finite and infinite, begin to dissolve. The mathematical beauty that governed the infinity collapsed the precise gravitational choreography that allowed two galaxies to dance together in perfect harmony, while giving birth to spacetime's most extreme curvature reveals deeper truths about the universe's aesthetic principles. This cosmic artistry operates through the interplay of symmetry and asymmetry, order and chaos, creation and destruction, weaving patterns of meaning that transcend purely physical description. The silence that now surrounds the newly formed black hole is not empty, but pregnant with potentially the gravitational field, extends infinitely through space, while the event horizon marks a boundary beyond which time itself takes on new meaning. This cosmic quiet contains within it all the future interactions and evolutionary processes that will unfold as the black hole continues its existence across cosmic ages. The memory of the collapse event becomes encoded in the geometric structure of space-time itself, where the curvature created by the black hole's mass preserves permanent information about the creative act that brought it into existence. This geometric memory will persist as long as the black hole exists, serving as a monument to the universe's capacity for self-transformation through gravitational collapse. The electromagnetic radiation that carries news of the black hole's birth across cosmic distances creates expanding shells of information that will eventually reach the boundaries of the observable universe. These photons serve as cosmic messengers that announce the successful completion of direct collapse, while carrying detailed spectroscopic information about the physical conditions that characterized this extraordinary event. The gravitational waves that propagate through space-time at the speed of light create permanent alterations in the metric structure of space and time, leaving behind memory effects that persist long after the waves themselves have passed. These geometric signatures provide lasting evidence of the collapse event while demonstrating how local processes can create global consequences through the fundamental connectivity of spacetime. The philosophical meditation on cosmic creation reaches its deepest expression in the recognition that consciousness itself participates in the universe's ongoing creative evolution. The human awareness that observes and contemplates the black hole's birth becomes part of the cosmic process through which the universe develops self-understanding and meaning through conscious observation and interpretation. The aesthetic appreciation of cosmic beauty, the recognition of elegance in the infinity pattern, grandeur in the scale of galactic collision, and mathematical perfection in the gravitational dynamics reveals consciousness as the universe's means of experiencing its own creative achievements. Through conscious observation, the cosmos becomes both artist and audience in its own ongoing creative expression. The temporal transcendence achieved through contemplation of cosmic timescales dissolves the artificial boundaries between past, present, and future that characterize ordinary consciousness. The black hole's formation becomes simultaneously an ancient event observed across billions of years of light travel, a present moment of scientific discovery, and a future influence that will shape cosmic evolution for eons to come. The spatial transcendence that emerges from cosmic perspective dissolves the boundaries between here and there, local and distant, self and universe. The gravitational influence of the supermassive black hole extends across cosmic distances, while its formation affects the global properties of spacetime itself, demonstrating the fundamental interconnectedness of all physical processes. The recognition of unity within apparent diversity, how the collision of two distinct galaxies creates a single merged system, how the chaos of gravitational interaction gives birth to ordered structures, how the violence of collapse results in the serenity of stable space-time geometry, reveals the underlying coherence that unifies all cosmic processes despite their apparent complexity and diversity. The ultimate peace that emerges from this cosmic contemplation transcends both activity and rest, both creation and destruction, both existence and non-existence. The black hole represents the universe's achievement of perfect gravitational harmony, where all forces balance in exact equilibrium, while maintaining the potential for ongoing creative evolution through interaction with its environment. The eternal now that encompasses the black hole's existence operates beyond the temporal boundaries of ordinary experience, where the event horizon creates a region where time itself becomes space-like and causality takes on new meanings. This temporal transcendence provides a natural meditation object that carries consciousness beyond conventional concepts of duration and sequence. The infinite depth of the gravitational well created by the supermassive black hole offers a metaphor for the infinite depth of cosmic mystery, recognition that every answer reveals new questions, every discovery opens new realms of investigation, every moment of understanding creates new appreciation for the vastness of what remains unknown. Now, rest in this cosmic peace, where ancient galaxies have completed their dance of creation, where space-time itself has given birth to its most extreme curvature, where consciousness merges with the infinite patience of cosmic time, feeling the profound stillness that emerges when the universe demonstrates its capacity for perfect gravitational harmony. Let awareness drift into the event horizon of deep sleep, where time slows to the rhythm of cosmic evolution, where thoughts dissolve into the perfect darkness of gravitational collapse, where consciousness experiences the ultimate rest that comes from witnessing creation itself in the eternal silence that surrounds all black holes, the perfect peace that exists beyond the reach of light, beyond the boundaries of time, in the infinite depth of cosmic rest. Sleep now, in the gravitational embrace of cosmic time, where billions of years pass like gentle breaths, where consciousness merges with the fundamental rhythms of space-time, where dreams unfold at the pace of galactic evolution in the perfect darkness that nurtures all light, the eternal rest that follows all creation, the infinite peace that encompasses all existence forever and ever and ever. Amen.